Hello, I'm pleased to have the opportunity to talk to you about our tritium mapping today. But before I begin, I'll just acknowledge my co-authors, Stu Hamilton from the OGS, Alex Lemieux, formerly of CNL and now with CNSC, Dave Rowan from CNL, and Ian Clark from the University of Ottawa. So I thought we'd start with just a little refresher on tritium. So just a reminder to everyone, it's a radioactive isotope of hydrogen. It's the common form of hydrogen has no neutrons, but tritium has two, so it's heavier. And it becomes part of the water molecule, so it ends up being quite a conservative tracer. And there are three sources of tritium in the natural environment. One is cosmic or cosmogenic, which is formed by neutrons from cosmic radiation blasting nitrogen in the upper atmosphere. And then we have nuclear plants, which are point sources of tritium, and they release tritium through steam and water. And then we have thermonuclear or bomb tritium, and that's what we think of when we think of tritium tracers. The source of this was weapons testing in the early 1950s, which peaked in 1963 and then tapered off. And what we're going to be doing today is using tritium to do groundwater age dating. And when I'm saying groundwater age dating, what I really mean is the time since water went from being rain to being groundwater. And using tritium is a great tool. It's unreactive in the subsurface, moves with groundwater flow, and because it has a known decay, we can use that to estimate recharge timing and quantities. So here I'm showing you a plot of tritium and precipitation from a long-term monitoring station in Ottawa, the Ottawa GNIP station. And what really stands out is that 1963 bomb peak, which was a key time marker and tracer used to estimate groundwater velocity. But since then, the peak has receded in precipitation records, and we can see that here as fallout has decayed and as thermonuclear weapons testing has stopped. And the peak has also been assimilated in most groundwater systems by decay and dispersion. So we see in this plot that tritium in Ottawa precipitation is relatively stable. There's still some fallout decay happening, but it's pretty negligible. So the loss of the bomb peak as a time marker means that we really don't have a good handle on our tritium input function across southern Ontario, outside of where we don't have precipitation monitoring. And so that means that to estimate groundwater age with tritium, you also need to sample for its daughter product, helium, which can be costly and tedious to collect. So our research objectives are to investigate the suitability of using shallow groundwater as a T-naught for estimating groundwater ages in deeper systems. So to use shallow groundwater instead of precipitation. And then finally to just make some groundwater age estimates and assess how reliable they are using this method. So our study area is 95,000 kilometers squared, comprising southern Ontario, and typically a precipitation input function is used for this type of groundwater age dating that we're conducting here. However, we have so few precipitation monitoring stations, and they are shown as purple triangles, relative to point source nuclear generating stations, which are shown as red circles. But what we do have a lot of are groundwater data from the ambient groundwater geochemistry program, with a tritium sample collected from each of the sampling locations shown here with gray and black dots. But we have to ask, is it reasonable to use shallow groundwater as a proxy for a precipitation input function? Well, it is if we can demonstrate that they are indistinguishable from each other. So a quick step back for a minute just to mention the ambient groundwater geochemistry program, which Stu talked about earlier. The northern work was done by our colleague Kayla Dell, the boundary shown in red, and our study area boundary that I'm talking about today is surrounded in blue. So in southern Ontario, in our study area, 2,516 wells were sampled. So our challenge was to create a subset of the complete data set that represents shallow modern conditions, those samples that most closely resemble rain. So we did so by establishing some selection criteria that includes aquifer type, well depth, well type, and overburden thickness for bedrock wells. So from the 2,516 wells, we ended up with a subset of 630 wells that represent shallow modern groundwater conditions. So once we had that subset of shallow groundwater wells, we interpolated tritium concentrations across the study area. And here we're showing the results of that interpolation, also with tributary data, which are shown as dots, and precipitation, which is shown as raindrops. And also, in addition, Great Lakes tritium is shown with contours. So blue is background tritium, which is about 15 tritium units, and red is the highest observed tritium in all of the color ramps used. So there's two real take-home points from this slide. First is that the nuclear plants in Ontario have a localized effect on tritium in shallow groundwater, and we can see that. I'm going to just move our symbol showing where those are. And second, that tritium concentrations in all the hydrologic system components shown are really similar to each other. So we can assume from this that the shallow groundwater data set is pretty closely linked with tributaries through surface water and groundwater interaction, which makes sense given what we know about the basic hydrology. So finally, just in previous work done by Brown at Atomic Energy of Canada, they showed that tributary data are a very good proxy for annually averaged precipitation trends. So given the good agreement that we're seeing here between tritium in shallow groundwater and tritium in our tributaries, shown with the dots here, it's reasonable to assume that shallow groundwater is also a good proxy for precipitation. But let's take a closer look. So here we're comparing tritium trends in Ottawa precipitation data from the GNIP station again against the shallow groundwater data for the same region over the same time period. So groundwater data are shown in blue and precipitation in black. And what we see are overlapping histograms that differ really narrowly in peaks and ranges. At the low tritium end, the shallow groundwater data set contains a few samples, 7% of the total actually, where the precipitation doesn't reach that low, but at the high end they match well. So generally the good agreement between the two data sets supports the use of our shallow groundwater interpolation as a proxy for a precipitation T0. So now that we've convinced ourselves that shallow groundwater is a good proxy for a precipitation input function, we're going to make some groundwater age estimates. So our T0 is taken from our shallow groundwater interpolation. That's where we get that tritium number. And then our tritium at time T is the tritium concentration in the subcropping bedrock groundwater sample. We have about 1,300 of these in the study area. And we know the half-life, which is 12.32 years for tritium decay. And then we solve for time, which gives us the number of years since recharge occurred. So our simple exponential decay approach comes with many assumptions, and I'm going to run through them here. So we assume that our shallow groundwater T0 interpolation is spatially representative and temporally consistent since at least the 1990s, when groundwater tritium in the Ottawa area in precipitation was stabilizing. Also, another assumption, groundwater movement has to be described as piston flow, so no dispersion and mixing, and that all tritiated waters were recharged post-1990s, and everything prior to that would have had little to no tritium. So these assumptions hold up differently for various groundwater age ranges, and the most reliable estimates that we make are for the youngest waters. Despite the varied reliability, these estimates are a really good start, and they show relative differences in recharge timing across Southern Ontario. Although I could talk about the assumptions at length, I'm only going to focus on the piston flow assumption, and we have some evidence to support that assumption is valid. So we sampled 179 wells more than once over a period of 8 years. And here are the resamples shown by location. We divided up the study area into southwest, central, and eastern Ontario. And in this plot, I'm showing you the first sample from the x-axis versus the repeat sample on the y. And the lines surrounding the one-to-one line that I'm showing represent analytical precision, which was estimated with a Thomson-Howarth error analysis. So 85% of the pairs, the resample pairs, fall within the precision envelope. And this tells us that tritium is stable over time in precipitation across the study area, so the input into the groundwater system, despite spatial variability in inputs. And the piston flow assumption is valid over this time period, which is 8 years. So the last few slides of my talk, I'll be just showing you some of the groundwater age estimates that we've made. Here I'm showing the youngest waters. The waters recharged from 2010 to 2018 are shown with blue dots, and 2000 to 2010 are shown in yellow. And these youngest waters are found in clusters that are associated with areas of rapid recharge in karst, which are represented with black polygons. So those karst areas were delineated with an empirical tool using threshold proportions of dissolved CO2 and O2 in conjunction with Frank Brunton's karst mapping. And we see that these youngest waters are really clustered within those karst areas, except where we have some Precambrian outcrop just south of Algonquin Park. And here we're showing the oldest waters, those recharged prior to the 1950s, overlying the drift thickness map. So what we notice is that the old waters are really present underlying the thickest overburden sediments, and definitely those samples are located outside of our rapid recharge areas identified in karstic zones. So in the east, we see these older waters underlying the Champlain Sea muds, north of Toronto underlying the Laurentian Valley sediments, beneath the Orangeville and Waterloo moraines, and also underlying the Norfolk sand plain. Also, in addition, we do see some older waters on the north shore of Lake Erie, where we see evidence of older waters and brines, and it's an area of known deep fluid migration. So definitely associated, older waters associated with that. So this is the final map I'm going to show you, and it really just brings it all together. This is groundwater age in the subcropping bedrock aquifers, and showing all the trends in one map. So our youngest waters are in blue and our oldest are in fuchsia. So even though there were a lot of assumptions tied to the method, applying it consistently across the study area gives us a really good picture of spatial trends and relative ages, at least for the last 70 years. So what's most interesting is that the trends can really be described by understanding the range of geological controls on groundwater residence times across southern Ontario. So just to sum everything up, we really took a close look at spatial and temporal patterns in tritium across the hydrologic cycle. And we saw a close connection among those components, and that validates our use of shallow groundwater as a proxy for annually averaged precipitation and a precipitation input. So our simple approach to groundwater age estimating using our shallow groundwater T0 highlights the geological controls on age distribution in the subcropping bedrock, and it makes sense. The results make sense. So our next step is really to publish the shallow groundwater layer, our T0, as a map and a KML in Google Earth, and publication will also include all the data and details about data selection and the interpolation statistics. So thank you very much for listening today, and please feel free to reach out if you have any questions.